So I thought about different ways to bring the course to a close, and some of the stuff that we are just going to miss out because this course is so constricted time-wise, and I already feel like I have shoved so much at you guys in such a short period of time. I wish we had had time to go through stuff like groundwater behavior and resources and contamination, mineral resources and how we excavate, mine, or otherwise prospect for minerals, oil resources, and I guess though with this point in time, maybe the oil thing is starting to become less important. It has been a real driver of geology education for so many years. And then, of course, in a more general sense, environmental contamination and climate change are very important to me. So all those things we're really not going to have time. So I thought maybe instead of picking one, I would do a thing where I try to tie everything together and look at our state, Georgia, and what the geology looks like here. First of all, through time, and then tomorrow's lecture, I'm going to look at across spatially across the state. So for today, Georgia geology through time and this idea of paleogeography. And I guess that means old maps in a way. So paleogeography of Georgia and where the state was, or at least the rocks that became this state through geologic time. So recall back at the beginning of the course how I talked about you should have a geologic time scale of one sort or another, so you could refer back to it. And I guess maybe I didn't refer to the time periods as much as I had hoped throughout. Well, I'm going to kind of make up for it now and talk them all the way through. So dig that thing out wherever you put it, and have that thing available. I'm going to have a little side key as we go through this, but you're probably still going to want to be able to context it to see where that is relative to everything else. This is Dr. Railsback at UGA. This is his version. I kind of like it, but I'm going to admit I'm not going to use it because it's not as familiar to me. But it does a really good job of showing how compressed the amount of time that we deal with is. And so this is the Cenozoic out here on the right. But really, if you compress it equally, it's just this little blue part right here compared to the Paleozoic, Mesozoic. But then again, you can take all three, Paleozoic, Mesozoic, Cenozoic, and compress them down, and they're just these top three little bits of the history of the Earth. Remember, we started out the course talking about 4.6 billion years ago, the planet starts forming. And you have this called this Hadean era, where I guess Hadean, they're just trying to say hell on earth here, because there's nothing livable here. It is molten mostly at the surface. We've still got major planetesimal impacts going on, all kinds of stuff. This is not a planet that you would recognize, or even that life could have evolved on at that point. And then we're going to get into, well, in the paleogeography, we don't get into the Archean. The Archean, there might be some rocks left over from the Archean, but they're very few and far between, and they're not intact anymore. We don't have any continents left over from the Archean or anything, or any large slices of things. Then finally, we'll start into the Proterozoic, and we have some of this. And so we'll deal with what little bit we have of the Proterozoic, but maybe some old animals. There's a big change from the Proterozoic, and I'll talk about that when we get to it. But these are something very old, a very old kind of life. And this is more how I'm used to seeing the timescale broken up, and you can see that they're not equal for these four different blocks. The Cenozoic is much shorter than even one of the bits of the Mesozoic. So, but this earliest on the right, this Precambrian, is where we'll start. Now, the term Precambrian, it's a little interesting the way we use that, because one of the periods down here at the bottom of the Paleozoic, meaning the oldest part of the Paleozoic, is the Cambrian period. So one of the ways we group it is Precambrian is just everything that came before it. We could talk about the Hadean down here, the Archean, and the Proterozoic. But right now we're just going to call it the Precambrian, everything before the Cambrian. We don't have much to go on in that time period. We'll start there. And I'm going to take each of these individual blocks as we go, and so I'll only be focusing on one at a time. But remember, you get Precambrian to Paleozoic, old life, Mesozoic, middle life, and now Cenozoic, the new life. And I wanted to talk about where I'm getting a lot of these reconstructions from, and I'm cobbling them together from several different sources. So this is all going to be still images as I talk through it, instead of trying to have things moving around on the PowerPoint slides, because this probably is going to be big enough when I try to upload it as is. But you can go to these websites here, and you can play around with these things yourself. This guy at UT Austin has a lot of the work out there. It's really neat to look around on his site, and he has a lot of stuff. If you go onto the 1122 course, I'm sorry, it would be very useful to look at the ecology, the paleoecology of the different time periods too. Another one I wanted to mention, and this software here, this is new to me this semester. I have never used it before. And neat thing about it is it's free, and it's real modeling software. So you're actually using the same sort of modeling gear that scientists would use to try to model and figure out what plate tectonic simulation looks like, what the plates really are doing, and trying to model that and figure it out. And anyway, both of these you can get to for free, and I would encourage you to do that if you don't have anything better to do after this course is over. So lots of pretty colors on this slide, of course, right? Well, let's talk a little bit about what's going on here. So basically, this is color coding by time period. So you have up here, this purple color is Archean stuff, or at least Proterozoic stuff. This is, I mentioned in a previous lecture about the craton, the Canadian craton. This stuff is very, very, very old. And it's exposed up here where the glaciers have scraped it loose, scraped down to it, and basically eroded away all the other stuff that might be on top of. We have some other old places. Up here is some in the Scandinavian peninsula, and then here there's some neat stuff in Venezuela that's exposed. You actually have we typically think of karst systems as developing on carbonate rocks. Those are the ones that would react to acid when we tried. And they're so soluble that they'll make holes. They'll make caves, they'll make sinkholes and stuff like that. Well, then here in Venezuela, you have quartzite. Now, quartzite, is a metamorphic rock, and how hard and tough it is, right? Well, that is so old that you have karst forming in quartzite, actual caves and sinkholes in a quartzite bedrock, and that's just a really, really weird thing. You see some really old stuff here on the Indian subcontinent. It's one of the reasons we know that it is a continent of itself. That and the Himalayas here, of course, where it's colliding with the Asian plate. You can start to make out a lot of the patterns of what's going on and how we're going to reconstruct these paleogeographies. You can see right here in the middle, you can see the age of the mid-ocean ridge spreading out from the center there, and some other ridges along different places. So the yellow is the latest stuff, and then the other colors are in-between colors, and we're going to walk through those. And this is that same image, actually, just zoomed in a lot. And so you'll see that, at least in their color scheme, and what do they have? Basically the yellow is Cenozoic, and then other stuff later than that. Mesozoic, I guess, is the green here, although their colors get a little off. But and then this is the Paleozoic. Well, Georgia sits right there across that. So we've got some of this new Cenozoic stuff down here, just a little bit of Mesozoic stuff, and then a lot of Paleozoic stuff up here at the top. So we're going to walk through that, and we'll talk more about that in tomorrow's lecture with the different spatial stuff. But we're going to keep up with where Georgia is as we reconstruct movement, paleogeographies. Okay, and here's our time scale again and the whole thing. Now, remember, we're going to start with just this Precambrian over here on the far right. I'm going to zoom in on it and use a marker system. So we're 560 million years ago, and we're late in the Proterozoic. We don't have much of this Archean stuff to work with, and so we're going to just be talking about what's happening right before we transition to the Paleozoic. I want to talk about where we are, right? So where is the Georgia thing? It looks like we are right here at that cross is marking the South Pole. So this reconstruction, and there's some argument. Scientists never agree on things completely, but in this model at least, this puts us basically where Dalton is, almost right at the South Pole, 560 million years ago. Right as we're about to transition into the Paleozoic. Now, I want to talk about what's going on right there at this break between the Precambrian and the Paleozoic. So I asked another professor recently a thought experiment question. I said, what species has done the most chemical damage to life on this planet? And the immediate answer was, well, I suppose that's humans. And actually, it is not. So at this time period, when Dalton is sitting at the South Pole, our atmosphere has almost zero oxygen in it. It's got a lot of carbon dioxide and some other interesting gases going on, but no oxygen. And so what life there was on the planet had evolved to work with that environment. Now, it turns out that oxidative stress is one of the big things that goes on in chemistry. And for oxidation potential, fluorine is the strongest of the easy to come by stuff out there. So fluorine, if you have fluorine gas, it's going to oxidize absolutely everything. That's the strongest on the periodic table, but the second strongest is actually oxygen. So it turns out that oxygen is extremely toxic to most of the ways things could have evolved. And all of this life that was on the planet before this point had evolved absent that oxygen. Well, then you have this organism evolves called blue-green algae, and they find a way to use oxygen as a sink for their electrons, and basically they start dumping electrons and making diatomic oxygen and pumping it out into the atmosphere. Well, when they do that, they basically poison everything else that can't handle that and kill off most of the life on the planet. Very, very little life other than the cyanobacteria survived. There are a few that we find at some of the deep smoke vents in the ocean. Dr. Hazel Barton has talked about finding some in some of the very, very deep caves on the planet. And these are usually called extremophiles because they don't work with the planet as it has evolved now. They're from what we consider a more extreme environment, but they considered, of course, a more normal environment. So here we are. We're still sitting down here close to the South Pole. The equator is way up here away from us. We're 550 million years ago. We're about to transition. We're about to have that oxygen catastrophe where it kills off everything, and we're going to transition into a whole new form of life and a new part of the table here. So here we are at, we're into the Cambrian period now, and we've had that extinction event where most of the life on the planet has died due to the oxygen in the atmosphere poisoning it. Let's see, we've moved a lot further north, and we're sitting here. You see, though, that what would be us doesn't really exist yet. So basically, there's just open ocean. There's a little bit maybe underneath some of the other parts of the U.S., and maybe even some early stuff exposed up here. Now, of course, where it's exposed is being eroded and going away, so that changes things. But maybe some limestones being deposited just a little north of us, but they're really, really deep now, and we don't see them. So what's going on during this period life-wise? Well, the new life that's starting to evolve after that big extinction event is some of it has shells. We're starting to see the very, very first versions of corals, some crinoids like you saw in the cave fossils. We're starting to see one of my favorites, the trilobites, are starting to emerge in the lower Cambrian here, and so you have all new life going on. Now we're going to talk about other extinction events as we go, but this one is neat because we actually know what happened with it. Sometimes we don't. With this one, though, we know for sure that it was that oxygen poisoning event that changed life on the planet completely. Now we're later in the Cambrian period, and you see that we're down here still. And now here's the equator, and so the South Pole is over here to the right, and then the northern hemisphere will be to the left. The continent seems to have rotated, so that basically we are rotated 90 degrees, so we're facing south that way. And we still don't exist. You can see how much of this was a sea, how much of it had been eroded away during the Cambrian. And now we're right at the end of the Cambrian. And there actually is another extinction event at the end of the Cambrian. A lot of these things were originally put together because of fossil changes, like when you see all the fossils here in the Cambrian suddenly change to something else. They'll mark that sometimes as a change. We're moving now from the Cambrian into the Ordovician period, and there are a few Cambrian rocks exposed up here. We'll talk about the Rome Formation. It's probably Cambrian. The Knox dolomite is probably being deposited during this period, although it might or might not be a dolomite at that point. But it's being deposited late in the Cambrian and early in the Ordovician period. So at this time marker, 485 million years ago, the rocks actually that I'm sitting on right now at my house would be being deposited at that time period off this coast right here. There's a little bit of land there. We're off on this edge of the shelf here. And here we're in the middle of the Ordovician period. We're at 470 million years. Notice how much more of everything is covered with water. And sea level has risen, and we call this a transgression as opposed to a regression. So sea level has transgressed further onto the land. More of it is underwater, but shallow. You see how this right here is all just a nice shallow sea? That is a great, great place for life to develop. The open oceans it's not great for life, really. It's kind of desert-like. I know it seems strange to call it a desert when it's water, but there's not a lot going on out there. But on the shelf you get coral communities, you get lots of fish, you get other, you get shell creatures, all kinds of stuff going on. You get nutrients from the land, all kinds of stuff going on. So this is the Ordovician period. We have a lot of limestones preserved up here in this area, in the Dalton area, and over here on the other side of the mountain, we have a lot of Ordovician limestones preserved here. A lot of limestones are apparently happening because of this shallow shelf being mostly covered with water because of that transgression. You see even more transgression here where we've got, we're later in the Ordovician, and you see a lot of stuff going on here. There's kind of a deep spot up here in Michigan. So we are, what will be our continent eventually right now is mostly covered by sea and has limestones being deposited on it because everything is, remember that limestone wants to develop offshore, and we're so far from where stuff could get eroded that it just can't get all the way down here where we're at. So it's nice clean water, shallow shelf where you can get sunlight in, and you can have a lot of life going on there. But now at 430 million years, we're in the Silurian, and something drastic has changed. So I think we are, I'm probably not up to date on everything, but I think we're still not exactly sure what all happened in the Silurian. But basically, sea levels dropped drastically. That could have been because the water got tied up in ice, or it could have been because of something changing with the magma circulation patterns and the kind of floating a little higher. But either way, more of everything is exposed, and you get when you get exposed. Now remember, we have this new oxygenated atmosphere. So when we're exposed up here, we're turning any of our iron-bearing rocks and minerals. We're oxidizing those to that red oxidized iron version. And sure enough, the Silurian, when we identified the ironstones or iron sands in the mine sample in the sedimentary rock lab, those were Silurian red sandstones, and that's happening while this is all exposed, and so it's being washed off either from the south here or from the north and deposited in here, and so we're not far enough away at that point to have good limestones developing. We have these red oxidized sandstones being deposited instead. So you start to see the idea that I'll talk about later about how we reconstruct these things. It's by the rocks that we have now, and so we know from some of the cross beds we can tell what direction stuff was coming from. We know how close it was by the rounding of the sedimentary grains, by that oxidized flavor. We know that it was exposed subaerially, that means to the oxygen of the atmosphere. And so we start to reconstruct a history of the planet based on the rocks that we have now. And here we are at the end of the Silurian, and you can see how much more that's closed up and sedimented in, and everything here is that red sandstone, and it's being oxidized by the oxygen environment. But if you go some further north, what's going on up there? You've got some big inland seas, but offshore here you've got maybe an island arc. And so if you could see the rest of what's going on, it might be that we have some plate tectonics going on and starting to push from the east here. It's actually, I think it's still south, but it's rotated around so it looks like it's east. But you have Africa coming up from the bottom right here and starting to push things onto the continent and cause a lot of changes here. But this is the end of Silurian. We're about to get to the Devonian. So we're in the Devonian, but back during the Silurian, a neat thing had happened. So we had all that land had been exposed, and nothing was going on with it. During the Silurian, a brand new thing happened, and life colonized that exposed land surface. Now, we're talking about some of the early plants that were starting to grow. Now the plants are just out here everywhere. And a new thing is happening in the Devonian where these really, really efficient animal creatures start to also invade the land to take advantage of all the plant material. And this is the insects. Insects really, really get going. Now, I'm not going to say that's the first of them. I think they actually may have evolved in the late Ordovician, but Devonian is where they really, really get going. So we're here still, mostly water, a little bit of the Devonian up here in the top. We're starting to develop this big inland sea here, the Catskill Sea. And we're still in the Devonian. We've got some land plants colonized here. Now we've got insects running around everywhere. We're starting to get lots of massive, massive fern tree swamps, stuff like that during the Devonian. And then at 360 million years, we're at the end of the Devonian, and we have another one of these extinction events. Lots and lots of stuff on the planet goes extinct. We're not real sure why on this one, I think. Of course, we still have some changes. May be related to sea currents changing. You can also see sneaking into the picture here, this is Africa, or what will soon be Africa. But it's closing this ocean right now and is about to slam into this, what will be the North American continent eventually. Now, while it's doing that, we've got subduction zone stuff going on. So think about our rock types to tie that back to that. So we've got a lot of compression happening. We're probably metamorphosing some stuff. We probably have a subduction zone, this dark blue color that you can see a little bit in here. that's probably very, very deep ocean, like the Marianas Trench off the Philippines right now. It's subducting what's left of this plate, this oceanic plate, is going deep down under here and probably coming up as volcanoes. So you've got a lot of that going on. So you've got some igneous rocks forming here. You've got definitely some metamorphism going on. So lots of strange stuff. But back behind this island arc, we probably still have a fairly quiet depositional environment, and we get a lot of swamp deposits back here, a lot of our black shales. So we'll talk some tomorrow's lecture about the Chattanooga Shale. Basically it's a source rock where we could have had a big oil deposit here develop, except for we lacked a good cap rock to capture it. And maybe we didn't bake it out enough. There's also a question about that. But definitely we had the characteristics to form it in the first place. Okay, now we are into a new period after the Devonian, after that big extinction. And so our big life form going on is probably starting to be amphibians. And some of these amphibians were really, really giant. Let's talk about this time period here, because you see, unlike these others, it has this weird one solid one on one side and a broken one on the other side. And that's because in Europe, they tend to just call this entire period the Carboniferous, where over here in the States, we tend to divide it into two different parts, the Mississippian and the Pennsylvanian. And that's because things changed, and it has to do with this plate tectonics that I'm about to talk about, right in the middle for us, where it may not have changed as much over in the European continent, which is off the screen to the right. So it's not getting as much going on. It's not getting as much action right now during this Carboniferous, according to them. But we're in our parlance, we're calling it Mississippian. Okay, and I talked about Mississippian limestones a lot. Well, that's what's being deposited right here in this shallow sea, back behind this mountain range. We're getting the Mississippian carbonates. Lots of limestones. These are where my caves eventually are going to form. We do have amphibians. I think it's kind of neat that we find amphibians a lot now in our caves, and this was the period when amphibians were first evolving. Now that's not why. It's just a neat coincidence to me. Now another thing to look at is, because we have plate tectonics going on, we have Africa coming in here. We're still pushing down. You can see this dark color in the sea there. That's that big subduction zone, really, really deep maybe, and it's shoving this last bits of this oceanic crust down underneath. You got volcanoes, and there's some volcanoes forming along this line here. So that ash layer that I showed you guys when I was showing the video from in the cave comes from these volcanic eruptions that are happening because of this subduction zone. So off the coast here, well, this being the main part of the continent at this point, this is kind of an island arc off the coast that looks a lot like Japan. And so those magmatic events bubbling up in here are going to have eruptions that are going to deposit those ash layers that we then find. Like I said, this is how we reconstruct this, by looking at the rocks that we see now. And we have to build backwards and try to figure all these things out. It's a giant jigsaw puzzle. All right, here we are right at that break point that we make over here in the States between the Mississippian, where my limestones are, and we're about to break to the Pennsylvanian. Now, a big thing that happens in the Pennsylvanian is a whole new form of life evolves, maybe from the amphibians, maybe from something similar. But we get a new thing, and this is the evolution of the reptiles. The first reptiles emerge in the Pennsylvanian period. And we're about to get an abrupt change as to what's going on here. Remember, we're at limestones right now. Okay, and now suddenly look what's happened to the land surface. We've had another regression where the sea levels have gone away. This time it probably is. We've had the big impact. And look at these giant mountains that are forming here. And these things would have been way, way bigger than the Himalayas are now. There would have been something there much, much higher than Mount Everest. Because you've got all of this slamming into all of this instead of just the Indian continent. We're kind of on the fringes of that, but we're uplifted. There's a lot of shear going on here. Maybe the big myelinite zone is happening where we're getting the cataclastic metamorphism that we talked a little bit about is happening through Atlanta. We've got shallow seas back here, but we've got a lot of exposed land also. So what's happening is where we had that nice clean environment for limestones during the Mississippian, it's not like that at all anymore. We get big chunky sands, those conglomerates that I showed you that we identified in lab. Those are Pennsylvanian in age, and so that means it was really, really close to the source rock. We get a lot of those cross-bedded sandstones, some of them red. We also get a lot of coal. And so most of the coal that we mined previously in this country comes from these basins, these sedimentary basins that come and go all along this area. And they're really shallow, swampy, and that's where the coal swamps were forming. So that's where we get this. During the Pennsylvanian, most of the coal that was found here in the U.S., at least in the eastern U.S., maybe out in the Wyoming stuff as well. All right, here we are at 300 million years. So we're at a break between the Pennsylvanian to the Permian. And I guess this break is mostly because of the tectonics here. Because see some weird stuff going on up here. This is mostly a downflex where Africa is slammed into this part of North America, and it's basically warped a big piece of the continent down right here. And then over here, we get so much going on. This is such a giant mountain range through here that we get, well, we have a really, really good marker actually in northeast Atlanta for what's going on here. 300 million years is the age of the Stone Mountain granite. So you have this giant granite pluton that was melted, probably partial melting from that old subducted slab and this very, very thick mountain building orogeny. This is the Appalachian orogeny. And you get melted out granites. But this one's a giant, giant granite that never made it to the surface. It cooled as remember this from our igneous rocks, it cooled as a pluton or an intrusive igneous rock. And that's why the crystals in it are so large, right? But we can date those crystals with, I think we usually use I don't think we've done a little bit of uranium with that one. I think we mostly do potassium dating with that one because of the potassium feldspars are so common in it. You can get a lot of data coverage. But you can tell from how crinkled up this is here how big these mountains are, and back here you've got that sea behind it again. We're moving into the Permian period. Well, 290 million years, and we're well into the Permian period now. And so if I didn't have these labels on here, right, and I just said, well, where's the North American continent and where's the African continent? Well, not so sure. Turns out this is South America down here, North America here, and Africa is over here. But this is Pangaea. This is how it formed, where Africa slammed into us here, creating this really, really big mountain range. And all that plate tectonics going on, and basically sutured together these two continents. You've got everything contained. This is Pangaea right here. So remember that we still, at this point, we're still Paleozoic. So all of this that we've had so far, to give you a scale, dinosaurs have not even started yet. Here in the Permian, we had the reptiles emerge during the Pennsylvanian. Here in the Permian, we get something called therapsids, where we're starting to get an idea towards what's going to become some dinosaurs. But they're definitely not dinosaurs yet. We still have mostly formed Pangaea here. Maybe South America's starting to think about breaking up this relationship. But we have a very, very big continental body here. A thing to think about with what that does with weather and climate. So think about where the biggest deserts are on the planet today. They're across that swath of Africa, Saudi Arabia, and then up through Iran and Afghanistan into the Mongolia area with the Gobi Desert up there. So that area, as desert as it is, it's got access to the Mediterranean there and the Red Sea and the Persian Gulf and everything. So it does have access to some water sources. And what I mean by access is that you'll have rainstorms float across it because of that. But look at this, how much of the planet, how much of the continents are completely away from water. So this is probably an extremely arid area across through there. And then, of course, you've got the mountains here in the middle. We have a lot going on. And that's how we start to reconstruct this, by looking at the different the paleogeographies that we can find. We can find pollen data in this, lots of different things. So we're reconstructing. Right here, we still got giant mountain range across most of Georgia. And 260 million years ago, we're late in the Permian, and look what's happening. We're starting to have a break right here. This is a rift, like we see in Africa forming now, but this is between Africa and North America, where it's starting to rift. Something has changed about their positions, and they're starting, instead of slamming together anymore, now they're starting to pull apart. South America is about to go off on its own down here, and we're starting to get a breakup of Pangea, that stuff that Wagner saw so many years ago. Well, this is where it's starting to happen. All right, geographically, we've got some stuff going on here. We're at 245 million, so note what has happened. Suddenly, I've shifted the time scale from that Paleozoic now to Mesozoic. We're at the bottom of it. We've moved into the Triassic. Well, what's happened? So we moved from Permian to Triassic. Now, you've heard about extinction events so far. I've talked about a few at the end of the Devonian, at the end of the Proterozoic, into the Cambrian. But as extinction events go, this was the big one. The Permian to Triassic literally probably extincted maybe over 90% of the life on the planet. So we think it's like 96% of the marine species died. Lots of the land species died. And the land stuff you can kind of see. We see the reverberation of that, because remember, we had just developed therapsids in the Permian. Well, if everything dies off, or almost everything, suddenly you have lots of stuff available, lots of niches, ecological niches, that are unfilled. Like, you don't have a predator. You don't have a big plant-eating species. You may not have very many plants anymore. So everything is wide open, and suddenly you get this explosion of new kinds of life, and that's where the dinosaurs come into the picture. You get dinosaurs here starting in the Triassic, and they're colonizing a lot of this stuff. But a thing to remember is that the extinction event was probably even worse in the oceans, and so you get new stuff forming in the new kinds of fishes, new kinds of corals, new kinds of everything in the ocean, even down to the plankton level, because you had such a major extinction event. Now, what caused it? I don't know that we even know this with the PT boundary. We don't think it was. I mean, there are a lot of stuff for the later ones, like an asteroid or stuff, but we don't have really good coverage. The biggest thing that's happening, though, you're seeing that with the geology here. We have, right here, we still have Pangea formed, right? And we're starting to break it up. So we're about to have a major change from all this continental environment. It's a really harsh, horrible environment. We're about to change that. We've got rifting going on. Something has probably changed about the magma circulation or the mantle circulation. Lots of things changed on the planet, and maybe life had trouble keeping up with those changes. And here we are well into the Triassic. Now I want to look at something that happened with those rifting. So do you remember that South America was trying to get away earlier? Apparently it failed. So there it is. There's the edge of South America, or what will be South America. And that rifting that was going on up there, maybe not, right? So this happens with rifts. They start to form and die out, and try again, and so a lot of that was going on. And so the volcanics that could have been involved in that could have drastically changed the climate on the planet with volcanic eruptions and everything. A lot of stuff could have been going on with this, but now late into the Triassic, we're getting the radiation of the dinosaurs and a lot of the plants that start to form during the Mesozoic period, and so stuff is starting to recover at this point. And here we are late in the Triassic, and this might be the point where mammals first evolved. We're not sure, but they definitely weren't occupying much of the space. The dinosaurs were taking center stage. Um, but you're getting a lot more life, and you're getting a lot more development along these rift valleys. Think about the Dead Sea and the rift in Israel, and you get a lot of these blind, small basins, and so maybe you have a lot of salts forming and stuff like that. And now we're at the boundary from the Triassic. We've moved just into the Jurassic period. And notice that most of this Mesozoic, we've had Georgia exposed, and so it's being eroded. Nothing new is being deposited here because it's exposed to weather, and it's being weathered. All the rocks are being weathered, and then once they're weathered, they can be eroded away. So you're not getting new stuff, new deposits forming out in the oceans, like we did in the Mississippian, because there's no ocean here. So it's all being eroded away. You've got dinosaurs proliferating more during the Jurassic, of course. Middle Jurassic, now you can see the rift is forming again, and it's going to try to get away. South America is trying to get away again. Maybe it'll make it this time. But there's your rifting, and we're still exposed. We're not getting any new rocks here in Georgia. And here's where the breakup happens. So we're Middle Jurassic, and now we have suddenly an open sea zone between South America and Africa and North America. We're still not exposed here, so we're not getting any of the cool rocks deposited. There are some magmas being developed here. This is what will become the Mid-Atlantic Ridge eventually. It's very, very small at this point, but you have a seaway opening right here in between. You see another basin back there, and that's where a lot of those Wyoming coals are coming from during the Jurassic. You get some stuff going on, but we're not getting any real new rocks here. Still nothing for us, but you can see a lot's happened now. We're further away from Africa. We have actually an ocean here now. It's not wide like the Atlantic Ocean, but traveling across this ocean here would be about like the distance, from Dalton to, say, Memphis or maybe St. Louis, something like that. So it's not as big as oceans get later, but we do have a significant body of water now in between. And now we're into the Cretaceous, the early Cretaceous, and this is really the peak of the dinosaurs. This is where the Cretaceous is really where they reach their peak. With apologies to Mr. Spielberg, the Velociraptors and the T-Rexes and all the cool stuff, Compsognathuses and stuff from the Jurassic Park movie, unfortunately, were not Jurassic at all. They were mostly Cretaceous. But I guess Cretaceous Park just doesn't have the same ring to it. So anyway, we have nice new ocean formed here. We can see a mid-ocean ridge in it. We have this interesting piece that broke off here, and so the stuff underneath Florida, if this is still extant, if it didn't get eroded away, if it's still there underneath Florida and South Georgia, you can see that it was actually a part of the African continent that sutured along Atlanta, and when we broke away, it came with us instead of staying with Africa. So there's a big part of the original African continent still underneath South Georgia and Florida there. A little later on, and you can see some stuff happening out west now. They've got a subduction zone going on out there, and they've got some mountains start to build up over there. All right, so now we're well into the Cretaceous here, and we've got the ocean here is opening nicely. We've got a good Atlantic forming, but we've got this shallow seaway that's starting to happen back here because you got a subduction zone and it's pushing up stuff right here. This big open area here would have stuff living on it. Well, so this is Cretaceous, and you probably have stuff being deposited in this, and so these are the Dakotas right here, and so you're thinking, well, we had lots of dinosaurs, right? Cretaceous, and then we're having a lot of deposition, sandstones, and then shales, and then limestones. Would be a really good place to have fossils build up of those dinosaurs, and it turns out that some of our best fossils for dinosaurs do indeed come from the Dakotas. And that's why that happens, is because you get a good depositional environment forming right there on that shallow seaway. We've closed that up some now, and the deposition is further out in Wyoming. Wyoming has some dinosaur fossil areas too. A lot of good mosasaurs out there where these guys were in a shallow seaway and just eating all the good stuff that was growing, all the good fish and stuff that were growing there on that shallow seaway. Now, here's a neat thing to see. We're late in the Cretaceous, and now we get some subsidence or transgression. We get some transgression of sea levels going higher here in Georgia. And so now we might get some deposition, right? And it turns out we do. We do have some Cretaceous chalks down at the fall line. But look at this structure that's starting to develop here. See that bite that goes in right there? That is interpreted to be an ancestral version of the Mississippi River. So way back in dinosaur times in the Cretaceous, we have that big river starting to develop there. And this is called the Mississippi Embayment. You see how it takes up most of the state of Mississippi underwater here. And this curve right here is going to be preserved. We can still see that curve preserved in the rocks now of what was already existing and weathered all during that time versus the new stuff that's deposited after that. Get some shift in the Mississippi embayment here, but it's still definitely there. Maybe had a breakthrough of the seaway over here on this side. All right, 65 million years, that's another big break point. And we've shifted from Mesozoic to Cenozoic now. We're back down at the bottom of the Cenozoic. And, 65 million, that Cretaceous, which we use a K for, to Tertiary, and you see the word Tertiary buried in here, is most of the Cenozoic is Tertiary. So we call that the K for Cretaceous, T for Tertiary, the KT boundary. That's the extinction event for the dinosaurs. And so we lose them at this point. We still got the Mississippi embayment going on. Still got some stuff going on with some limestones being deposited there. But just like the therapsids and the reptile world went extinct and made way for the dinosaurs, it looks like, at least this is the classical interpretation. I think there's some questioning of this nowadays, but it looks like the dinosaurs went extinct at the end of the Cretaceous and made room, made vacant all the niches they had been occupying, and this new group of animals called mammals start to take over the planet. See where we are here, and this is Paleogene, Paleocene. There's some unfortunate overlap of terms here. Tertiary or just Cenozoic to tie it all together. Tertiary you probably want to have heard of at least. And here we are, and you can see that the continent is starting to develop something that we could recognize more. So we're still sitting right there. Florida is kind of chunky right now. The Mississippi River looks more like it's a river now instead of a big giant bay. This is the Caribbean, right? We can start to recognize that. You can see the Yucatan Peninsula sticking out here. Mexico's developed, but you can see that we don't have a Baja Mexico. So we don't have much of a San Francisco Bay. But a lot of this continent is stuff that you would recognize. There's Greenland. You can see Europe over here now, and Europe is closer to us than Africa did. And here we are at 50 million years. We're into something called the Eocene. The Eocene, a lot of the rocks are rocks is a loose term there. At least a lot of the sediments that we might be convinced to call rocks are preserved in Florida. You see that Florida is underwater here, and there's a nice Eocene marine clay that we can find in most of Florida. Um, so it was a shale type deposit, shale facies. Still no Baja California. 40 million years ago, we still have no exposed Florida. We do have some giant islands here where everything's kind of stuck together there in the Caribbean off the coast of the Yucatan. 25 million years ago, we're seeing a lot of things. We're now in the Oligocene epoch, and there might be a little bit of Florida starting to poke out above the water. Most of it's still below. But it's now, most of the Oligocene deposits that you find in Florida are sands, not the marine clay that like we had in the Eocene. So you're closer to the shore, maybe some uplift going on and a lot of erosion off of Georgia and deposited there in Florida. You see a little bit going on down here. The Caribbean is taking shape that we would notice. You can see this is 25 million years ago, so this is way too early for any peoples to exist yet. What is the? I don't remember. I'll have to look it up before I start the next slide about what the primate evolution looks like. I don't know where we're at. 25 million. I'll look that up. But definitely no humans yet, or nothing resembling humans. And so here is where Georgia is. Okay, so yeah, I went and looked that up in between slides there, and so it looks like we did have some old world monkeys show up maybe at the end of the Eocene into the Oligocene, and then you have your first apes were maybe showing up at the beginning of the Miocene. So that Oligocene to Miocene is at 25 million is important for primate development, and we're not at hominids yet. I'll point that out in a second. But so Miocene, we're still maybe developing the first apes. They're over in Africa, where you can't see off here off the right side of the screen. Let's see what we've got going on geologically here. We've got some tectonics starting to develop. You can see a trench off the coast of Mexico here, and that probably gives us some of the volcanics that are still happening there. Florida is still being mostly deposited with, with clastics, although we get a lot more silts with the Miocene in Florida. Then you get a definite river system developing where the Mississippi will be. I guess it is technically the Mississippi at that point. You get some breakup of the islands here in the Caribbean, so you're starting to see a lot of things, but you still have this convergence between, it's called Beringia sometimes, but you get the plate has stretched over, and this is all North American plate stretching over into the Asian plate on that side. So we had hit from this side, and now we've bounced and come all the way across and are starting to make contact up here in the Bering Sea again. And here we are getting closer to the end of the Miocene, 8 million years ago. We're almost ready to evolve the first hominins over in Africa. Hominins with an N, not with a D. Those are even later. So you see we've got some stuff going on here. And then this is neat to see right here. You can start to see a major delta starting to develop off the coast of that Mississippi River here. So you're starting to get deposits that we can reinterpret here and see what's going on. You still get this major basin formed here. And look at this, you get a development here of that Baja California Sea, and then maybe this is the development of the San Andreas and stuff is starting to shift northward. That whole piece is broken loose here and it's starting to slide to the northwest. And that transform fault right there is what's given us some development of the topography on the west coast right now. So now we're at just 3 million years ago. We're in the period is still Tertiary or Neogene, but we're in an epoch called the Pliocene. Next is going to come Pleistocene. You've heard of that before because of Ice Age. This is the Pliocene just before that. Looking at the geography, this definitely looks like a North America that you would recognize. Now, something seems to have happened to Florida still. It's still underwater and still getting stuff deposited. Poor old Florida down there. But most of this, you can see that the outline of Mexico is nice and intact. A little bit of stuff going on with the Baja Peninsula. You even have, if you look right there, you've got the valley and the San Francisco Bay. It's much bigger than the San Francisco Bay that we have now, but that sediments are falling in that right now at 3 million years back, and so you get a lot of stuff that you would recognize if you could go back and visit this version of the planet. So hominin-wise, in Africa, we actually now have, if you've heard of the Australopithecus species, we're starting to develop, well, genus I should have said, not species. We're starting to develop stuff that look like a lot like us. And so this is just 3 million years back. Think how far we have come at this point. And here we are well into the Pleistocene. Pleistocene, you know of as a glaciated time. This is the great giant ice age, 0.125 million, or easier way to say that probably is only 125,000 years ago. So this is extremely, extremely late in the history of the planet. We're almost to the present. You see how much of the planet is covered in ice at this point. Europe is even worse off than here. Ice is reaching down. It's not quite to DC or St. Louis, but it's getting fairly close. Here's the position of Georgia, and Florida has finally poked its head above water. But what's happened with that is because so much of the water has gone and gotten in the ice caps that there's less in the oceans. That's why Florida is exposed at that point, because of the ice caps holding a lot of the water, and so sea level is relatively low at that point. You get a lot of stuff that you can recognize. The San Francisco Bay is a lot more like what we would expect, although we probably have some connected drainage on further in what's now desert. Australopithecus has emerged over in Africa. Here's South America. South America has rotated up weirdly here. I'm not sure I believe that part of the reconstruction. But that's there's a lot that can be argued in these reconstructions as we go back. 125,000 years. And this is Pleistocene. And here's our situation today. Our sea levels are a little lower than they were. I'm sorry, a little higher than they were during the Pleistocene, because not as much of the ice exists anymore. And of course, that's changing drastically right now. As far as epochs go, there's an interesting controversy going on right now in geology. So it's hard to see, but I hope you have your own, of course, to look at. So we're definitely out of the Pleistocene we have been in the Holocene period. So the Holocene period goes back 12, 15,000 years, and that's where mankind has colonized the planet with our genus and our different species. We've colonized the planet and really started to take over from everything else. Now, there's an interesting thing. If we look for, so we talk about the KT boundary at 65 million years when the dinosaurs went extinct. And if you ask a geologist, hey, is that 65 million? How closely do you know that? And I think most geologists would say, well, you know what? I don't want to be constrained more than plus or minus at least a million years. Give me that much leeway. A million years to us seems like a big time frame, but when we're trying to reconstruct all this from rocks, it's not that much. Now, with the Holocene, a lot of geologists now will argue that there's a brand new period called the Anthropocene. The Anthropocene would postdate the Holocene, and unlike wanting a million years, we can actually point to the hour where it changed. We know precisely where it changed. And isotopically, when we look at isotope dating, the biggest single change at one point in time, isotope-wise, on this planet, happened when we dropped nuclear bombs. It changed the entire isotope signature of all of the radionuclides in the atmosphere at least. Hopefully not in the rocks. We can still use them to do some dating. But anything after 1945, we cannot use carbon dating anymore because it is so off at this point. Because we've changed the chemistry of the planet so drastically at one instant in time. And so I would argue for a new Anthropocene epoch, but that is definitely not a unanimous thought right now, and geologists love to argue this point with each other. So that's where we are now. Next slide. And talk about tomorrow's lecture will be about surface geology, and that's how we get all the information, and we're trying to reconstruct all those things I just showed you come from looking at surface geology. So next time will be, how do we do that? How do we reconstruct?